In this lecture, we will learn about the fundamental case of structural reliability, where the resistance or strength of the structure is described by one parameter R and the load are described by one parameter S. Both these two parameters are assumed to be normal distributed. We will also introduce the Cornell's safety index beta. A very important property of normal distributed parameters is that if x1 and x2 are two independent normal random variables with mean mu x1 and mu x2 and standard deviation SDx1 and SDx2, then the sum x1 plus x2 will also be normal distributed with mean mu x1 plus mu x2 and variance SDx1 squared plus SDx2 squared. If these variables are correlated, the variance is corrected by the covariance, but more about dependent variables later. Another interesting thing to discuss is the normal distribution and the so-called Z values for this. The standard normal distribution is a normal distribution with a mean value of 0 and a standard deviation of 1. A Z-score describes the position of raw scores in terms of its distance from the mean when measured in standard deviation units. The Z-score is positive if the value lies above the mean and negative if it lies below the mean. It is also known as the standard score because it allows comparisons of scores on different kinds of variables by standardizing the distribution. In structural reliability analysis, we are always evaluating rather small probabilities, way lower than 50%, so all our Z-scores will be negative. The probability associated with Z-scores can easily be calculated in Excel. The way to use standard normal tables is that if we want to find a probability associated with the Z value of, for example, minus 2.3, we find the value minus 2 and minus 0.3 on the horizontal and vertical axis respectively, and we find the probability that is associated with this Z value, in this case 1.07 times 10 to the minus 2. Normal distribution tables are found in the literature and may look like this, but as already shown, these can easily be created in Excel, or the probability can be directly calculated for a given Z value. So in our problem, if we have strength that is normal distributed and load that is normal distributed, we can define the safety margin M equal to the strength R minus the load S. Following the property of the sum of normal distributed parameters, the safety margin M will also be normal distributed with a mean value mu M equal to mu R minus mu S, and the variance SDM squared equal to SDR squared plus SDS squared. The safety margin M can be illustrated as shown in the red dotted line. The probability that R minus S is less than 0 can then be written as the probability of the safety margin being less than 0. So the problem is simplified to calculating the probability of the value of a normal distribution being less than 0. As always, we can do that by integrating the normal density function from minus infinite to 0, which is by definition the cumulative normal density function at 0 for a given mean value and standard deviation. If we want to use Z scores or Z values, the Z value in our problem is then 0 minus the mean value of the safety margin M divided by the standard deviation of the safety margin M. which can easily be described by the mean value of the strength and load and the standard deviation of the strength and load. The probability of safety margin being less than 0 can be illustrated by the cumulative normal distribution inserted this Z value. Alan Cornell in 1969 introduced a safety index beta, often denoted beta Z, as a negative of this Z-score as a measure of the safety of structure. If we look at this in the distribution function for the safety margin M, the beta is the distance from M being 0 to the mean value of the safety margin M, measured in standard deviations of M. Some numbers of the beta value for important probabilities, such as 10 to the power of -1, 2, and so on, is shown here. Note that beta is close to 1 for probability of 10 to the power of -1, and close to 2 for 10 to the power of -2, and quite close to 3 for 10 to the power of -3. However, after 3 or at least 4, this similarity stops. In summary, we have shown the definition of the Cornell's beta index, which is a simple way of calculating the probability of limit state exceedance for two independent normal distributed variables. The relationship between Cornell's beta index and the probability of limit state exceedance have been established.